As you know, we calculated this integral before, but this time let's go wild and let's close the contour in the lower half plane as opposed to the upper half plane. So pause the video and try and figure out what changes. Okay, we're going a little bit quicker in this case because we have already calculated that integral in a slightly different way. But what we need to look at is the complex valued contour integral of the function dz divided by 1 plus z squared. But now, rather than closing this in the upper half plane, we're going to close the contour in the lower half plane and see what happens. Obviously, if you want to use the residue theorem, we need to figure out what are the residues that are inside our contour here. And this time, this will be a residue here at minus j. So we need to calculate here 2 pi j times the residue at minus j. So this is 2 pi j using the formula with the derivative. So we copy the numerator and we take the derivative of the denominator. That's going to be 2z, and evaluating that in the point, minus j, of course. If we calculate that, then we end up with minus pi. Okay. Now we're going to take the limit of this radius here, capital R, going towards infinity. And in that case, we can write down that this contour integral basically consists of two parts. First of all, we have the integral along the real axis. But this time it's going to be an integral from plus infinity to minus infinity, because we go from here to there. So that changes. So we have dx divided by 1 plus x squared, because we're back on the real axis. And then we have a contribution from this circular segment C capital R. And the residue theorem tells us that this together is equal to minus pi. Let's again focus on this part here, the limit of capital R going towards infinity. We don't have any exponential in our integrand, so this means we need to look at the big limit theorem. And for the big limit theorem, we need to consider the limits of capital R going towards infinity, and then also z going towards infinity, actually. So that's 1 over 1 plus z squared, not forgetting to multiply by z minus the origin of the circle, which is in our case 0. So since we have a higher power of z in the denominator as compared to the numerator, the denominator will pull the whole thing towards 0 if z goes towards infinity. So the whole thing vanishes, which also means that this contribution to the contour integral vanishes. So now we're in the situation where we can write down that just the integral from plus infinity to minus infinity is minus pi. Flipping just everything on its heads, we just pick up a minus sign to go from minus pi to pi. And now, again, making use of the observation that our integrand here is an even function, we can write down that the integral from 0 to infinity of dx 1 plus x squared is equal to pi over 2, which reassuringly is exactly the same result as we obtained in the previous exercise. So it doesn't really matter whether you close your contour in the upper half plane or in the lower half plane. In this case, you always get the same result, which is nice.